Hey everybody, welcome to problem 2 in lesson 4, where we use tables, graphs, and equations to compare exponential functions and quadratic functions. So in this problem, it looks like we've got two patterns, pattern A and pattern B. And I think the way that I'm going to go through this is to talk about pattern A first, and then we'll talk about pattern B. And if you've already done all these problems, then great. You already have knowledge about both of them. If you haven't, then feel free to follow along in kind of the order that I'm doing them, pattern A and pattern B. We are also going to do these problems in reverse order. So the three questions are: 1, write an equation. 2, is the function linear, quadratic, or exponential? And then 3, complete a table. We're going to do those in reverse order. So the first thing we're going to do is we're going to complete the table. The second thing we're going to do is we're going to decide whether the function is linear or quadratic or exponential. And then the third thing we're going to do is write an equation. We're going to write the equation last. You don't have to do it in that order. You can do it in whatever order makes sense to you. If you feel like you have the equation before the table, great, cool. I just want to give you a heads up that I'm going to be doing them in the reverse order. All right, so let's look at what we got. Bullet points. Bullet point. In pattern A, the length and width of the rectangles grow by one small square from each step to the next. So the length and the width get bigger each time. Okay. In pattern B, the number of small squares doubles from each step to the next. Okay. In each pattern, the number of small squares is a function of the step number n. So that third bullet point is should remind you of what we did in lesson 3, right? Where we said the input was the step number and the output was the number of squares. This is that same thing, right? This tells us that we want to find a formula that gives us a relationship between the step number you're on and the total number of squares in that step. So that's where we're going with that. All right, so pattern A and pattern B and the three questions. Now would be the time for you to pause the video, complete the table, decide whether you think the function is linear, quadratic, or exponential, and then see if you can write an equation for pattern A. And then when you're done with that, come back and we'll talk about pattern A. Okay, welcome back. So, table, easy enough to start. Step number, the first step number is 0. The next step number is 1. 2, 3 is the number of steps in the pattern, but if I scroll down, they want us to make a table that goes all the way to step number 8. So I'm going to do that as well. 4, 5, 6, 7, 8. Okay. The number of small squares we can just read off. So in step 0, there are 0 squares. And I don't know if that kind of caught anyone else off guard, but yeah, step 0 has 0 squares in it, which is odd, but is what it is. It was not a typo. Step 1 has 1 square. Step 2, 1, 2, 3, 4 squares. And step 3 has 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. So to go any further on this table, we're going to have to find a pattern. The pattern for this, they already described it, right? They say that the rows and columns get bigger each time. So like rows and columns kind of get added to the outside. But hopefully at this point, you also noticed another pattern, which is if you look at these things, they're each squares, and the size of this square is growing by 1. So this square is a 1 by 1 square. This square is a 2 by 2 square, and this square is a 3 by 3 square, growing each time, 1 by 1, 2 by 2, 3 by 3. You might have said or noticed a very similar thing by noticing that the 4 and the 9 are also perfect squares. 4 is 2 squared, 9 is 3 squared. Technically, 1 is 1 squared, and 0 is also 0 squared. 0 times 0 is still 0. So this should help you find a pattern moving on. So if the third step was 3 squared, then the fourth step is probably 4 squared, which is 16. Even if you didn't write these out as like 1 squared, 2 squared, 3 squared, and you just noticed that 1, 4, 9, and 16 were perfect squares, that's good too. So for 5, the perfect square is 25. For 6, 36. For 7, 49. And for 8, 64. And if you don't have your perfect squares memorized, that's fine. You can use a calculator or use, Google Calculator or your phone and just calculate these on your own. No, that's not a problem. So 25, just to complete the table, 5 squared, 6 squared, 7 squared, 8 squared. I asked this question before break on one of the weekly or the daily check-in questions about like, why do you think we call things where it's like 8 with a second power up here, why do we call them squares? And a lot of you guys are like, well, because when you do it, it makes a square, like 3 by 3 is a square. And I was like, okay, cool, yeah. I think that's where it comes from too. So yeah, that's it, right? Here's our table. Question number 2 asks, is this function linear, quadratic, or exponential? Well, just as a reminder, linear would mean we have to add by the same number each time. So we can annotate that, but we're going to quickly find that it's not true. To jump from 0 to 1 would be +1. To jump from 1 to 4, this would be +3. And right there I can stop because I'm adding a different amount to get from the first 2 steps to the next 2 steps. 0 to 1 and 1 to 4 isn't a linear jump. So it's not linear. Right? Should I write that down? So linear no, because it's not constant addition. Okay. The other options, quadratic or exponential. So quadratic, this entire thing we're doing right now is about figuring out what quadratic means. So if you're not quite sure what makes something quadratic or not at this point, I'm going to actually say like that's probably okay. And if you go back and you look at the last lessons and the titles and you go back and watch some of those videos, the theme that you'll notice for quadratic functions is when things are being squared. And so that kind of gives the game away, right? In this pattern, are things being squared? Yes. So then we say yes. It is quadratic because there is a squared term. Right. And that's it, right? So then is it exponential? No, because it's quadratic. And if we want to do better than that, we could say like, for something to be exponential, it's because there's a constant multiplier. This is digging deep in those memory banks, right? And so when we look at our table, is there a constant multiplier to get from 0 to 1 to 4 to 9? Like, are we multiplying by 2 or 3 or 4 or whatever? And the answer is quickly no, right? to get from 1 to 4, we'd need to multiply by 4. But 4 times 4 is not 9, it's 16, but the jump doesn't work. So there's no constant multiplier to get from one number to the next. So no constant multiplier. So it is quadratic, it's not linear or exponential. Okay, so now we're going to go back and we're actually going to do question number 1, which is to write an equation. So our equation, we can build from the pattern that we noticed in the table, right? The pattern seems to be you can take the step number, and when you square it, you get the number of squares. So I want you to listen to that again, right? Take the step number and square it to get the number of squares. And so an equation is just going to convert that sentence into a mathematical formula. And so what does that look like? Well, we said take the step number. The letters we're using for the step number, is n. So we're going to say take n, and what are we doing with it? Well, we're taking n and we're squaring it, and the result will equal the number of squares, which we're saying is a function of n. So equals f of n. And that's it. That's our formula. Most people would write it the other way. Let's do it like this. And by the other way, I mean in the other order. Like they would write the f of n first, and then they would say n squared. And that is your formula. Right? Take the step number, square it, and that will be your total number of squares. Okay, so at this point, I'm gonna pause the video, tell you to pause the video again, and we're gonna go and do the exact same thing for pattern B, which I have right over here. So pattern B, complete the table. Is it linear, exponential, or quadratic? And then write an equation. And just as a reminder, right, I'll scroll up in the thing really quick. Remember, we know that pattern B follows a particular rule, and the rule up in the table is, or up in the top there, says, in pattern B, the number of small squares doubles from each step to the next. So, pause the video, fill out the table, find an equation. Okay, welcome back. So let's fill out this table. In step 0, there is 1 square. In step 1, there is 2 squares. In step 2, there are 4 squares. And step 3, there are 1, 2, 3, 4, 5, 6, 7, 8 squares. Easy enough, but they want us to go all the way to 8 squares, or 8 steps, sorry. So 4, 5, 6, 7, 8. And to go any further, we need to find the pattern. Well, we know the pattern. Right? The pattern is that the number of squares doubles each time. Well, what does that mean? First there was 1, then there was 2, then there was 4, then there was 8. Do we see the doubling in our table? Right? What does doubling mean? It means times by 2 each time. Doubles to get to 4. Doubles to get to 8. So to get to the next step, what are we going to have to do? Well, it looks like we'll have to double again, which will get us to 16. To get to the next step, we'll double again. So 16 doubled is 32. 32 doubled is 64. 64 doubled is 128. And 128 doubles is 256. Now, if you are not comfortable with those doubles in your head, that's totally normal. As a math teacher, I know some pretty weird math facts, but I don't expect anyone else to know them as well. But if you do, Nice job, very impressive. No, you should probably be using a calculator. Times 2, times 2, times 2, times 2, each time. And that's fine, right? Use a calculator, not a big deal. So is this function linear, quadratic, or exponential? Well, based on the conversation we had for pattern A, this one should be pretty straightforward, right? The pattern or the rule is multiplying by 2 each time, and that is a constant multiplication, so this is exponential. That's what exponential means, right? So exponential yes, because there is a constant multiplier. The constant multiplier is times 2. Right? Not only do we know it's a constant multiplier, we can even be specific. We know the constant multiplier is times 2. And so all that's left is to make a formula. So now to do this, we need to do something we haven't talked a lot about, which is thinking about like, well, how many times 2's do we need at each step? So let's go think about like step number 8. And now to do this, you might be thinking all the way back to stuff we were doing first semester. This was things like the rabbit families problem, the mini poster project you guys did. This was thinking about making exponential equations, making explicit exponential equations. So if you happen to like have your notebook, you could be using that and going back and looking at the exponential problems back in unit number 3 to see some examples of what we're about to do. So let's think about this. If I want to get all the way to step 8, how many times did I multiply by 2? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8. Ah, so step 8 required 8 multiplications. Step 7 required 7 multiplications. Step 6 required 6 multiplications, etc., etc. So our formula seems to be that the total number of squares, right, f of n, comes from starting at 1, right, that's our 0 step, and multiplying by 2 however many steps you've gone. So if you've got 1 step, you would multiply by 1 copy of 2. If you have 2 steps, you'd multiply by 2 copies of 2. And that is the exponent. So the n up there tells us how many copies of 2 we need. If we want step 8, we would need 8 copies of 2. And that is our formula. That's it. Okay. So let's see if I can get these tables side by side. So this last question down here at the very bottom that my face is kind of in the way about, it says, how would the 2 patterns compare if they continue to grow? So we have step 8 here for the quadratic pattern A, which got all the way to 64. And we got step 8 here in the exponential pattern that got all the way to 256. So if we kept going, what would happen? How would they continue to grow? I think if you're making observations like, well, they would both continue to get bigger, yeah, that'd be good. The big observation, let's think again about our goal for the lesson. Right? The goal for the lesson is I can explain using graphs, tables, or calculations that exponential functions eventually grow faster than quadratic functions. So looking at these tables, does this exponential table look like it's growing faster? Yeah. And where are the observations? Well, you could say something like, well, in the quadratic, I see a 64 in step 8, whereas in the exponential, I see the 64 at step 6. Right? The exponential is already past it. Or you could say, I can see in the next step, the exponential is going to get even bigger than the quadratic. Something like that, I think, would make sense given our goal for the day. All right, that is the end of problem 2. Move on to the last video to go to the last problem of this lesson, and I'll see you there.